Morning. Okay. As Benjamin said, my name is Daniel Bodony. You can call me Dan. It's a pleasure to be here. I apologize for not being here earlier in the workshop. I just dropped my middle son off at university back in the US and took the flight immediately after. So thank you for that grace. What I want to do is spend the next 35, 40 minutes kind of describing what it is we do all around the idea of preCICE. And I'll talk a little bit about the infrastructure, then talk about the applications, and then come back to preCICE specific ideas. And I'm hoping there's a lot of time at the end so that we can have a discussion or a talk, answer questions. I'm happy to take questions in the middle also. So if something is not clear, something is curious, just stop me. I guess Benjamin has to run with the microphone, but I'm happy to answer those questions. So let's get started. So I'm going to focus on one aspect of our research, which is fluid structure interaction, specifically at high enthalpy conditions. So think strong shock waves, sufficient energy that you can ionize the gas, have radiation in that field, all for the purposes of aerodynamic predictions, as well as supporting material science and testing. And I'll describe those applications as I go. This is sufficiently complicated that I work with a large group of people back in the United States, many of whom are listed on the slide. And I want to acknowledge that they are the primary implementers of the ideas. They often come up with all the creativity. My job is relegated to managing, thinking about the projects, and then helping write papers. But of course, I spent a lot of time getting to that point. And I also want to acknowledge the funding sources for all of this work. It spans many federal agencies in the United States. I won't say anything more than that. The Department of Energy and several offices within the Department of Defense have been gracious sponsors of this work, and they continue to be. So I'm grateful for those the support. And also the National Science Foundation. In the United States, a lot of the computing resources come from the National Science Foundation, and we use all of their leadership facilities to make some of these calculations possible. So I'm grateful for that support as well. So I'm going to talk a lot of things in the space of hypersonics, and so I want to define what I mean by that before we get too far along. So many of you may be fully aware, but this slide documents the types of regimes of hypersonics. The left side focuses on air-breathing propulsion where the Mach numbers are high, Mach 5, Mach 6, Mach 10, but the chemistry is not very active except in the chemical combustor part. And so there, the primary goal of hypersonics is shock wave, boundary layers, and some heat transfer on the leading edges. As you go farther to the right, the enthalpy rises such that the chemistry and electrical structure of the gas become fundamentally important, not just carry along without much action. To the farthest right is satellite reentry, vehicle reentry through the atmosphere, where they're the only thing that is really important is the chemistry, ionization, radiation. So our main operation regime is between the first two pictures on this. I have colleagues who focus on the far right-hand side, but that is not my expertise. And I'll be using the Mach number as sort of a guide for this. For the types of things that I'm interested in, the vehicles that fly through the atmosphere at, say, Mach 10 or so, they experience a wide variety of physical phenomena that are of interest to me. And so I am first and foremost sort of an engineering scientist where I'm interested in the engineering application, but also the science that goes behind it. And we use large-scale computing to support that inquiry. As you read throughout the figure, you'll notice there are many different types of physical processes. Some of these are very unrelated to each other at the outset. Modeling them can be quite difficult. I'll call out a couple. One of them is mechanical erosion and spallation. So as one of these vehicles flies through the atmosphere, it can encounter any number of particles, raindrops, dust particles, and when they hit the vehicle at very high speed, they can cause localized damage. In addition, as the material begins to heat up, it starts to chemically change. And sometimes that chemical change leads to fracturing of the surface at the local level. And that leads to spallation of particles of the material surface into the flow. That is an extremely challenging and important area that I won't say too much about specifically. What has been driving us most recently are the ablation and shape change, where the interaction of the flow with the material causes the material to recess as the material goes through a pyrolysis process, outgasses, which cools the surface, changes the surface shape, as well as standard fluid structure interaction, where you have unsteady forces and thermal loads on a surface, a metallic surface, for example, causes the surface to deform. That changes the aerodynamics. All of those are coupled together, and those happen simultaneously. All of these often impact laminar to turbulent transition all at the same time. And one thing you'll take away from all of this is that there's many time scales and space scales that are of interest to us and which are driving the fundamental questions. And sorting out the space and temporal scales is a key challenge and is something that we use these multi-physics codes and preCICE to help us answer. So these are sort of the relevant physical processes that I use as a guide for some of our research. So the first thing I want to do is normalize what kind of infrastructure we're going to use to run these simulations. And then I'll talk about the application of that infrastructure. And then I'll come back to the infrastructure at the end. Right, so in one slide, this is our standard non-radiating, non-chemically active infrastructure. It is a traditional fluid structure interaction framework where I have the compressible reacting Navier-Stokes equations in a compartmentalized fluid solver. I have a thermo-mechanical solver that allows for nonlinear deformation, in-plane and out-of-plane stresses, full 3D finite element for the structure. These are all coupled together, and preCICE is the tool that we use to couple all these together. Each solver has its own time step, space scale. All of them are parallelized. All of them are built to run on the largest computers that we have access to. I'll call out a couple of things. For the fluid solver, we spend a lot of time focusing on turbulence and transition. So we pay close attention to the numerics that we use for handling shocks and turbulence simultaneously. So if you're interested about that, I'd be happy to describe it. But this is not finite volume style discretizations. For our thermomechanical solvers here on the bottom, we've moved to an infrastructure called MFEM, developed by the Department of Energy's Lawrence Livermore National Lab. This is an open source technique or open source framework that's very similar to DL2 and similar. We found it very profitable to use and have started to embrace it a little bit. Another thing that I'll call out is that we have spent time thinking about multi-rate time advancement, where we take advantage of this temporal scale disparity, and I'll describe those as we go. But this is sort of a standard fluid structure interaction framework for loosely coupled solvers that are connected together. When I say loosely coupled, this is what I mean. The temporal scales and spatial scales from either side of an interface are known to be different, and they can be dynamic. One of the things that we're exploring is event-driven coupling, where instead of having time steps between each solver, maybe one side runs for a long time until there's an event. And then you call a solver on the other side, and you have some exchange of data at that event. That spallation example that I gave at the beginning is sort of a hint of where that might be useful. But this is what I mean when I say loosely coupled. And a little bit more detail on the fluid solver infrastructure, because it was built from the beginning to be multi-physics. So the fluid solver itself can handle multiple grids. Each grid can have its own separate physical description of a problem. Don't have to solve the same equations in all the grids. And one thing that I will also highlight is that we spend a lot of time doing multi-physics linear analysis, meaning what is the linear operator that describes the linearized behavior of the entire system. And we found preCICE to be very, very profitable in extracting that linearized operator for some analysis, and I'll highlight that a little bit. Our codes are all built on standard MPI and OpenMP, but they also use backends like Cocos for hardware acceleration on different architectures. And when I say we run at scale, this is an example of one of the scaling runs that we've done with the fluid solver. So PC2 is one name for our flow solver. Speed up is on the vertical axis in a strong scaling sense. Horizontal axis is nodes. So each of these nodes has 100 plus CPU cores. And Frontera is the largest machine in the United States for education-focused supercomputing. The machine has 4,000 nodes. So we can run on the entire Frontera machine, 500,000 cores with this infrastructure. All right, so that's the infrastructure from a high-level sense. I'm now going to go into a couple applications of this infrastructure. And the first one I'm going to start off with is a traditional fluid structure interaction problem of interest to the United States Air Force. This is funded by the Air Force Office of Scientific Research. And the idea is you have a supersonic or hypersonic flow coming from right to left. It intersects this flat plate that has a nominally flat surface. And on this flat plate is a vertical fin that is angled several degrees from the incoming flow. And there's a shock wave boundary layer interaction scenario that is set up. The geometry of this problem is described by conical symmetry. So think spheres of origin sitting on this VCO, which stands for virtual conical origin. And if I take spherical shells of constant radius about that point, I get roughly conical symmetry in those planes, and we can document those coordinates with those two labels there. And so if I look in that spherical plane and I look at the flow that happens in that plane due to the shock boundary layer interaction, this is what we see. So looking at this little inset image, moving to the right, vertical is the phi, horizontal is the theta. There's a main shock wave that is created by the fin, but that shock wave generates a pressure gradient that separates the boundary layer. That boundary layer is roughly conically symmetric. And it creates this interaction region at the base of that shock boundary layer interaction. And one of the artifacts of that interaction region is a impinging jet. So through through this interaction, there's actually a supersonic flow that gets directed directly to the surface of the plate because of this shock boundary layer interaction. It would not be there if the flow was purely inviscid. And this impinging jet is known to lead to very high localized pressure and thermal loads on the surface, and is what our main focus of investigation was. So this is a computational study that has an experimental component. And the picture on the left is the experimental model that has been studied in the NASA Langley Mach 6 20-inch tunnel in Hampton, Virginia. And what we do is we take the CAD of that experimental geometry and use it as our base model for our calculations. I'm going to be describing purely aerothermal calculations, so we're not going to show results with the deformation of the surface in this presentation, though we have some if there's curious. And the primary interaction region is this green section, which is in the base of the shock boundary layer interaction and is precisely where the impinging jet occurs. So using the infrastructure that I described, what you're watching is an animation of 3 different flow conditions. The top 2 are at Mach 6, which correspond to the Langley tunnel conditions. On the left is a low Reynolds number version where the boundary layer is laminar. On the right is a high Reynolds number version where the boundary layer is turbulent. Of course, I just got those backwards, didn't I? The high Reynolds number is on the left, the low Reynolds number is on the right. The bottom right is a Mach 10, which corresponds to the Langley Mach 10 tunnel. Unfortunately, the tunnel broke, so we didn't get experimental data at the time. In the bottom left is the animation of the aerothermal process, right? So we're ignoring all the fast time scales of the fluid here, and you're watching the generation of the thermal state on the panel. And you'll notice that there's a very high region of heat flux into the panel, which corresponds precisely to that impinging jet location. You'll notice that the transverse thermal gradients are quite strong. Turns out that the transverse displacement of thermal expansion is just as large as the in-plane or out-of-plane displacement from the pressure non-uniformity. And as the simulation evolves over a 6-second physical time window, the temperature of the panel increases by approximately 100 Kelvin. So these are pretty substantial temperature rises over the time period. picking off different time instants, you get profiles that look like this. You'll notice that there is some conical symmetry in these profiles. So even though the flow itself exhibits conical symmetry, the heat transfer is approximately symmetric. And if I take a top-down view of only the panel temperature as functions of time, you get the high Reynolds number, low Reynolds number Mach 6 and Mach 10 case on the right. And you clearly see a distinction in the Mach numbers, even for the same Reynolds number. One thing I'll note is that these calculations were performed with SU2, the RANS code. And some things that are missing is that there are actually very thin vortices that streak from the upstream side to the downstream side that add additional heat transfer locality to the surface of the panel that are missed by a RANS model. I have those results in another slide if there's interest. All right. So that was a standard fluid structure interaction problem at high enthalpy, where high enthalpy meant high Mach number, not so much chemistry. What I'm now going to do is transition to a much higher enthalpy case focused on a facility called the Plasmatron-X, which is an inductively coupled plasma facility. There's a similar one in VKI. And focus on ablation. And really, it's about studying material response at very high enthalpies. And so this application is going to drive our multiphysics coupling in additional directions to support the very high enthalpy conditions. So this is a movie of the Plasmatron-X. So what you're watching is an iPhone video of the jet that comes out of the torch. And I'll describe all this as we go. But the purple region is a very high temperature ionized gas. The Mach number is about 1.2. The jet comes out of a straight cylindrical pipe and it's underexpanded. So there's a series of shock cells and compression diamonds. The temperature leaving the jet or leaving the torch is about 10,000 Kelvin. By the time it gets to the leading edge of the sample, it's cooled off to about 6,000, 7,000 Kelvin. During testing, these mechanical arms are rotated into the flow. And at the end of one of these mechanical arms, you see a sample. You can clearly see the radiation from the sample, and then they're tracking the heat flux at the leading edge of that sample through some data processing that happens later. Our goal is to understand the flow physics of the facility itself, as well as to understand the response of a material sample placed in that flow. So this is and for scale, the image, the sample size is about that far from the torch exit. So this is about full scale. So here's what the Plasmatron-X is. It's an inductively coupled plasma. It is a very simple device in that there is a cylindrical tube through which multiple ports are created for injecting gases of various types: air, argon, nitrogen, oxygen, carbon dioxide, for example. The torch has swirl added to it for flow stability. But most importantly, wrapped around the torch is a coil through which radio frequency electromagnetic waves are passed, and those joule heat the gas inside the torch. The coils operate at 350 kilowatts as their maximum power. Approximately half of that power gets dumped into the fluid. The interaction region occurs directly underneath the coils. Notice that the coils are helical, so they actually impart an asymmetry to the torch flow as it comes out. That turns out to be important later. And then the flow then accelerates as it goes to the exit. This nozzle has a converging diverging geometry shown. Most of the work is done with a straight nozzle only, which is what I'll also show. Once that flow leaves the torch exit, it intersects with the body. And you'll notice that the flow around the body is quite unsteady. One of the purposes of this investigation is not only to get the basic temperature, pressure, heat flux values on the body, but to understand that dynamic unsteadiness. Because it has been observed in the facility that at different operating conditions, the jet can be very unsteady. And that affects the heat transfer measurements, and that affects all the correlations that are done between the sample and its behavior in a high enthalpy environment. And I should state, if I didn't state it already, that one of the primary users of this facility is SpaceX. So SpaceX comes to our facility, tests their samples on their Falcon 9 and other rockets to understand their thermal behavior for re-entry and departure. So on one slide, this is very busy, but I'll walk you through it. This is sort of the operating space of the ICP. The vertical axis is power. So one of the variables we can control is how much power is deposited into the flow. The horizontal axis is the pressure in the chamber itself, so you can control that independently. At different intersections in this power pressure space, you get different behavior of the jet. And that different behavior is indicated by these images, which are XT diagrams of the emission along the jet center line. So if I take a picture of the jet and I record the emission of it to my eye, I extract only the center line, and then I make an XT diagram of that. That is what is being shown. And one thing you can observe is that as you change pressure at constant power, the red-blue regions change their structure considerably. They go from being relatively weak and uniform to being very non-uniform with a slope that is indicative of convective process. These green and red lines also indicate approximate boundaries in the behavior of the jet. The green line indicates when the jet exit is supersonic relative to subsonic for a straight nozzle case. The red line is one that is equally interesting in that to the right, the model of the fluid can be assumed to be in local thermodynamic equilibrium, or LTE. That means that even though there's chemistry happening, it's sufficiently fast and the non-equilibrium state of the gas can respond quickly enough that it's always locally in equilibrium. Whereas to the left of this boundary, we have to account for the non-equilibrium effects that happen within the gas. And this is where the time scales of the different rho vibrational states become important. Radiation becomes fundamentally important. And I have colleagues like Marco Panesi and others who are, that is their main thing, is to study and model non-equilibrium thermodynamics. Right, so what we want to do is use this coupling infrastructure to understand the flow in this environment. So how we do that is with this slightly modified version of the infrastructure that I showed before. At the center is a fluid solver. It's a standard finite volume solver that has been around for quite some time. What makes it most interesting are the things that it is connected to. So here the flow solver is just the bundler. Excuse me. For the non-equilibrium is Plato. It's a physiochemical library. It's similar in purpose to Mutation++, if you're familiar with that library. On the top, green, is the electromagnetic solver that controls the Helmholtz solve for the coils that surround the torch that produce the volumetric electromagnetic field that intersects with the fluid and creates the Joule heating. To the right is a thermomechanical response solver for ablation, which I haven't described yet, but I will in a little bit. To the left is MERP, or the radiation solver. That is the solver that is responsible for taking the flow results and converting them into a predictive spectra for radiation. Like, what are the emission lines at a frequency specific view, or what is the integrated energy in radiation, as you might pick up with your eye. All of these are connected and run simultaneously through preCICE. And the data that we pass back and forth is, in this case, is actually quite substantial. There's several variables that we have to pass through, all through volumetric coupling to make this work. And I'll leave this up there for a second. I'll say that we've spent a lot of time understanding what needs to be passed and the order in which the data needs to be passed and what data should be passed in which direction for both numerical stability, provable convergence, as well as physical modeling accuracy. We continually evolve this infrastructure as we work harder problems, but this is shown to be relatively robust, I will say. All right, so continuing on, this is an example of an axisymmetric calculation. where you have a schematic of the torch on the left. The chamber is shown in the movie on the right, and a nominal sample, this isn't a real sample, of course, is shown in the far right. You'll notice that this jet is very, very unsteady, right? So historically, these jets have always been assumed to be steady, and when flow solvers did not converge, it was seen as an error of the flow solver. These jets want to wiggle around and jiggle, right? They are globally unstable under certain cases. And you'll notice that the jet has a very unique structure. The density at the center line is 1/100th of the density in the chamber. And so these jets are very highly stratified. The standard Kelvin-Helmholtz instability that is common for more terrestrial jets is harder to see here. And entrainment is a massive component to the growth of the jet as you go downstream. And if you follow one of these black regions long enough, you can imagine that this black region, which is cool fluid, hits the sample, locally cooling the sample, changing the overall average temperature that the sample sees and changing the overall average heat flux that the sample experiences. And this is part of this is believed to be one of the reasons why the correlations of heat flux and temperature in the plasmatron were not matching other expectations based on steady flow assumption. Three-dimensionality is indeed important, and one indicator of that is the figure on the left. So the gray helices are outlines of the coil that wraps around the torch through which flux solver is used. The green and the blue colors indicate isosurfaces of Joule heating, so the rate at which energy is being transferred into the fluid by the Joule heating, and you'll notice that they are asymmetric. Well, the impact of that asymmetry is many-fold. One of them is it decouples the base thermodynamic state from the species that show up in the torch. So if you look at the pressure or the temperature, it is almost axisymmetric. But if you look at the species distribution, it is not, because it is much more sensitive to the local temperature state. And so we have to account for these asymmetries. Also on the right, you'll see a case where the subsonic jet was underexpanded, and you can see the shock cells that have been set up in that high temperature plasma condition. Those just document that. One of the challenges that we have and what continues to drive us to perform these simulations is that experimental diagnostics are limited. We really have few measurements on which we can lock our predictions to reality. One of the primary ones is radiation. So there's always a series of cameras that are used to observe the jet and the sample. And there are many ways in which you can extract information from those measurements. One of them is just basic intensity of the radiation as a function of distance. And each of these three figures describes a comparison between our raw predictions of the plasmatron using the infrastructure that I just described and measurements taken in the plasmatron with the camera. And effort has gone into modeling the camera, modeling the windows through which the radiation goes, accounting for three-dimensionality effects, and so on. And I'll highlight that Soon-Min Jo is the individual who's responsible for most of these predictions. And you'll see that we get fair agreement. We do not have perfect agreement. And we don't yet understand why we don't have perfect agreement. Other investigators at other facilities see similar comparisons. And there's a lot of uncertainty in the literature trying to model these plasmatron facilities from the basic engineering input parameters of power and pressure into actual predictions that are quantitatively meaningful. Now we are on this, in the sense of engineering, we are on the same scale. We're within a factor of 2 always. Generally, our trends are always correct, but there are times in which quantitative agreement eludes us. One of the interesting aspects that I have a few students working on is understanding the physical origin of these waves. And here I remind you that these images are space-time diagrams of the emission along the center line of the jet. And a slope of these lines indicates a convective behavior from downstream or from upstream to downstream. And the slope is the inverse of the propagation speed. We have measurements on the right, predictions on the left. There's rough agreement between them, so we get the basic convective velocity, but the physical origin of these modes is we think we know what it is, and we're dotting up that argument to make sure that we can conclusively so. But you'll notice that there is some spatial structure differences between the two images, right? For example, the interfaces on the simulation between red and blue are sharper than those in the experiment. Is that a consequence of the measurement? Is that a modeling deficiency? That part we don't yet know. Now, of course, the whole purpose of this thing is to put a sample in the facility. Excuse me, I got a tickle. And here is where we are running all of that infrastructure with, in addition, the ablative solver running simultaneously. So the image on this far right is the unsteady deformation of a porous material sample placed in the plasmatron jet with the torch simulation, the chamber simulation, and the ablation all running simultaneously. The ablation happens at a very short time, or a very long time scale compared to the jet. And if you watch this movie, whoops, play it again, there. Over the space of several seconds, say 10 seconds, the sample has moved approximately 2 to 3 millimeters. Right, on the scale of 180 millimeters from the sample head, from the torch exit. We're able to predict the temperature through various probes placed within the sample to a reasonable degree of accuracy. There is some sensitivity of the materials that we use, so the direct comparisons are difficult quantitatively. And I think I'll skip this for the sake of time. All right, so what I've now done is given you 2 different examples of how we use multiphysics simulations to look at high enthalpy flows. Now I want to talk about very briefly, some things about accelerating these. One of the key applications that we have is ablation modeling in the presence of boundary layers. So this is an example of a surface. It's a open geometry surface where at the leading edge of the interaction, the material is porous and it is allowed to ablate. As it ablates, the temperature and shape obviously change, but that also happens in the presence of instability waves that happen in the boundary layer. And it turns out that there's a phenomenon called differential ablation, or it has other names, but differential ablation is the big one, where if you put an ablative material in a flow, it will form grooves. These grooves have a structure. They look like waves if you go to the beach, you look at the sand gets waves in it. If it has a river coming over it, or from the waves from the ocean. That deformation of the sand is very similar to the creation of these grooves, but the physical origin of these grooves is unknown. And what we're interested in doing is being able to couple all of these features together, the instability waves and the boundary layer, with the ablation, which is an incredible time scale disparity, and trying to allow for these temporal scales drive some of our interest. So going back to this loosely coupled diagram, we're interested in accelerating the temporal integration across the interface. And one of the techniques that we've been toying with is developing data-driven models on the interface itself. So imagine running your coupled simulation and you've got a flow solver on one side, a structural solver on the other, or some other material response solver. And on the interface, you treat it as a dynamical system whose dynamics are coupled to the two but are independent of either. Can you come up with a faster acceleration technique for integrating that surface? And so the idea is you take your original dynamical system, you identify the boundary conditions that are the precise coupling conditions, and then you say, okay, can I take those data and project them onto a reduced rank model? Right? So this is like having a dynamical system on the interface itself, whose dynamics are driven by recovering from the data of the primary simulation some operator inference. And so the technique that we use is based on oblique projections, where these operators phi and psi correspond to encoding and decoding, if that's the language you like to use. And from these operators, we can come up with a lower rank system Z, where Z is a much smaller number of variables. Think like 10 degrees of freedom of 10 or 20 compared to thousands. A and H are operators that are learned as part of the simulation. And we optimize these operators during the calculation. So imagine a scenario where you do a time resolve calculation for a period of time. You learn these operators A and H, phi and psi. You run with the learned operators for a period. Then you relearn the operators as the simulation proceeds. And that learning and adjusting the operators leads to a measurable acceleration of the coupled simulation. And what I can show is that the techniques that we use are superior in terms of error, which is less important than we can show that we can recover 1/10 to 1/100th of the cost of this acceleration by this adaptive learning process. Another feature we've been using is to take the linearized operator, right? So we're used to running codes that are full nonlinear codes. Some of the tools that you have may be able to produce linearized versions of them through automatic differentiation or whatever. But what if we knew these linearized operators early on? Then a little bit of linear algebra shows that you can use concepts like the resolvent and the input-output operator who have structure that are directly relevant to what happens on the interface itself. And so the idea is that if I'm running a fluid ablation, sorry, I have this tickle that does not persist. I have a fluid domain in the exterior, the ablation domain near the body. The interaction between the two is very well captured by the input-output operator modes. So these are input modes, output modes. There's a singular value decomposition that can be used to rank them. And I can use that ranking to, again, compress the data on the interface. This is also very profitable for long time duration, multi-scale, multi-physics calculations. All right, so now I'm coming very close to the end, and I wanted to give a couple of specific comments on preCICE. One of them is, the first one is really thank you. I have written codes that do what preCICE has done for the last 20 years. It's miserable. Thank you. Right? preCICE is really the first tool that I've been able to use robustly. When this tickle stops, I'll be very happy. Because it no longer requires me to think about the code coupling. I can just say use preCICE and couple, and it's done. And I know that that happens not by accident. So I do want to say thank you for that. Bullet number 2 is about the Python interface, the PyPreCICE. This has been wonderful for our group's perspective. Because imagine that I have a group of graduate students and postdocs and research scientists, and they say, hey, I have an idea for something I want to do. Do I want to test that idea in the full multi-physics interface, or can I test it quickly? And Python provides a way to easily test some of these concepts. We have tested wall models for fluid structure interaction. We have tested different ablative models, multi-physics material models. We have prototyped these ideas. And as the Python as a linear analysis toolbox has become more the norm, you can now directly couple these linear algebra toolboxes through preCICE to your flow solvers without having to think about it. So this has been very beneficial for the analysis of flows and the prototyping of ideas. And to that latter point, I want to point out this. I did not anticipate using preCICE for analysis. I thought I was going to use it as a multi-physics coupling technique. We use it probably 80% of the time for analysis. So what we do is we use the volume and surface coupling capabilities to inject localized disturbances into our flow, take the difference of that disturbed calculation from the undisturbed calculation. I now have a difference. I now have a gradient. And I can do that in a strategic way and get the linearized operators for the entire multi-physics calculation. And I can look at the input-output operators of say the power input of the torch to the temperature at the surface of a material in the plasmatron, all within the same finite coupling framework without having to write new code. That has been very, very beneficial for us. And I advocate for that whenever you do it. An example of that activity is shown on the right. So this is a problem that I did not describe in detail, but it's not too difficult to do so here. There's a Mach 20 flow approaching a leading edge. This was an experiment that was done 30 years ago by NASA, where a reentry vehicle was measured, and they had temperature probes in the vehicle. And what we were wanting to answer was, why is this tickle persisting? We were wanting to answer the question, what is the role of the boundary layer state on those temperature measurements? And so for that, we had to understand the change in the boundary layer stability characteristics as a function of the vehicle flying through the atmosphere at Mach 20. To do that, we have to know what the boundary layer state is. To do that, we have to run the calculation along the trajectory. And at each trajectory point, we do a local linearization to get the local operators to figure out, is it globally unstable, convectively unstable, and if so, to what? That is in a primary example where we're passing non-equilibrium thermodynamic model data back and forth and using preCICE to extract a linearized operator that corresponds to that base flow condition. We do contribute, and so we've used SU2 quite a bit. We've updated some of the preCICE couplers that go with SU2. And I just got a request from our host here, because we use MFEM quite a bit to create some MFEM developed tutorials and coupling interfaces, because we use that quite a bit. And so we're very grateful to contribute back to the community from which we have benefited. So to close, I hope I've convinced you that we're studying several forms of this fluid structure interaction at high enthalpy conditions. That we have other problems that we use. I haven't described them all here. Doing so requires this very tight interaction between experiment and simulation and modeling these complex multiphysics simulation tools, of which preCICE is a core component. I didn't even go into a lot of the details, like what are the models for the non-equilibrium, material degradation models, surface catalysis, et cetera, which are some of the leading modeling questions that are being able to be answered by this infrastructure. And with that, I'll close and thank you for your time and happy to answer all your questions.
Thank you, Dan. Very interesting and very nice words, nice points. Who has the first question?
So I don't remember exactly which variables were now involved in the entire coupling, but especially for the free stream simulations, are there discontinuities carried along in your coupling data, or is this typically something you get away with?
So I believe the question is, do we have discontinuities that propagate through the coupling interfaces?
Yes.
We are generally scale resolving, so there are no discontinuities that come in. So shocks are the closest thing, but they get modulated by the boundary layer. So there are no shocks that hit the surface through the coupling interface.
Okay.
That is a great question, and we can talk about that separately, or in addition, if you want to continue.
Thanks.
Because okay, I can't resist. It actually, so shock waves are hard. And it turns out that the basic numerical schemes for propagating shock waves, like muscle, if you were to do the linearization of muscle, you get something that is not unique. And it is not convergent. And what that means is the adjoint of the linearized system is ill-defined. What that actually means is what you propagate as a discontinuity cannot be guaranteed to be accurate. So muscle may be able to predict the nonlinear problem, but it cannot predict accurately the linearized problem to a converged state. If you permit yourself some slightly different numerical schemes for propagating shocks, you can handle linearized shock waves very easily. Those can be coupled to preCICE, but we have not gotten to that point yet. There's a couple people in the world who are working on this. We have one, and Vasily Theophilus, if you know who he is also working on that.
Yeah. So maybe to add to this, so discontinuities could be challenging for the data mapping in preCICE. That's, I think, a bit where the question comes from. So would be nice for us to see like cases where this is needed, and then to study whether we can actually do this or not.
Yeah, I think that's a great question. And I appreciate that I don't understand all the origin of the question, right? If I treat a discontinuity as just a discontinuity, it's going to be very difficult because I don't have any constraints. But if I know I'm dealing a fluid dynamic system and there's a discontinuity, I know it permits certain kinds of discontinuities. And I know through analysis how I can embed that information in modeling the discontinuity itself. That's where there can be some benefit, but that may not be within scope of preCICE development. Do I have a fluid dynamic discontinuity? Do I have a material response discontinuity, et cetera? That's where you need some physical information to guide you on the arbitrary discontinuity.
You briefly mentioned multi-scale at some point in your talk.
Yeah.
Do you deal with drastically different length scales in any of the problems and couplings? And if so, how do you get across these?
We have not focused on dealing with them in the same way as the time scale disparity. So we typically over-resolve on one side of the domain. That just seems to be where we can put our intellectual heft, is on the temporal time scales, because that's what makes us wait, right, is solving that problem. Although, I can't resist, we've been talking about having DFT calculations. So, for doing very atomistic scale-ish modeling of the material and coupling those to our fluid solver. So now you're talking about a massive scale disparity. And in the event-driven comment that I made earlier was, imagine I want to run a DFT calculation to represent a material that has gone a very big change in state, and I need to know the new material response characteristics. Can I do a localized DFT calculation, have that represent a region in my space, and then average up back to the resolved scales of the calculations? So those are on our mind, but we haven't focused on them yet.
Yeah, I have a poster which is a software solution for that, so maybe we can talk about it. Yeah,
I'll take it.
Thank you for your talk. It was very interesting. I have a question on one of your earlier slides. I may be wrong, but I saw that you are using a Cantera in some of your setups. Could you describe how it is integrated in the whole simulation setup? Did you cannibalize the software, or is it integrated as a whole component?
Sure. So the question was about Cantera and how do we use it. We actually cheat. We have a tool that takes Cantera and creates a C++ version of only the mechanism we care about. Then that gets embedded into our flow solvers, rather than carrying along the entire Cantera. And so there's a library that is available for you if you wanted to use that to do it. But we avoid the entire heft of Cantera by extracting the only the mechanism that we want. So we automatically generate code from Cantera and embed that into our flow solver.
Okay, thank you.
Thank you for a really nice talk. Lots of interesting stuff. So this surface ROM that you were talking about, I find that quite fascinating, but I didn't really understand how exactly are you using it?
Sure. Here, I'll just go back. Oh, I need a nice image. This is good enough. Oh, come on. Where's the boundary layer? There. This is good enough. So imagine that I want to model what happens at the interface. And let me give a couple scenarios to motivate it, then I'll answer your question directly. Right, so imagine that I want to do a long time calculation of the material, which is ablative material, and CHIPS is the name of our solver for it. Imagine I want to model this boundary layer that forms. But I don't want to carry along the flow solver because that carries a lot of cost and a lot of timescale disparities. So from the side of CHIPS, can I learn what the exterior flow is trying to do on the surface? Well, I can if I permit myself the following scenario. Imagine I'm going to run the flow solver and the chip solver simultaneously for a little while in time. And I use perturbations that I design to extract some fundamental behavior. Think of like extracting the Green's function for that interaction. I use preCICE to couple the two codes. I extract the data on the interface. Now I have this time-dependent interfacial data that connects the current state of the material to what the flow is doing on the exterior. With that data, I now have inputs into an operator inference model. An operator inference, all it is say, given this time-dependent set of data, there must be some operators that connect the evolution of the data as functions of time. Proper orthogonal decomposition would just say, find me the primary directions. Tools like dynamic mode decomposition would come up with a similar dynamical or a simpler dynamical model. Oblique projection is superior in that it gives you the autoencoder and the decoder are no longer required to be orthogonal to each other. All that to say, I can come up with small operators A and H that represent the fluid action on the material in the absence when the solver is gone. Now I can take this surface ROM and replace the flow solver with it. Now I can run the material response solver with a model for the exterior without having to actually run the exterior fluid model. That is one idea we have pursued. And I know that as the material evolves, those operators A and H have to evolve also. So I allow for there to be some streaming learning that goes where I constantly evaluate A and H. And you can build a schedule for that learning, that adaptive learning, and then it just runs automatically. So imagine you run a calculation. It starts by having all the solvers run simultaneously. It does the learning that it needs, develops the model, stops running the most expensive solver, runs with the reduced solver for a period of time, checks its local error as it goes along. There are ways to do that. And then relearns those operators, continues on. And you can do a fire and forget kind of model for that. So we have done that for these fluids.
So you're learning a dynamic Dirichlet-to-Neumann map for the fluid.
For one side. We chose the fluid because it's the more expensive side. But you can do this for any time you have two time-dependent solvers running simultaneously.
Thank you.
Sorry, can I just follow up? So you said you have a good estimate. You have an estimate for the error, or you know the error in your reduced order?
We have an estimate. So
Okay.
if I know the flow state, I can compute the right-hand side. I also have a prediction of the right-hand side from the reduced order model. It's easy to estimate the right-hand side. It's also easy to compute the right-hand side. The difference between those two is an error estimate.
So you said you schedule it, but do you not just reuse the full model when your error breaks a certain bound? Or,
Exactly.
Oh,
So
okay,
that's exactly what we do. We say, okay, if error greater than fraction of percent, relearn. Exactly.
And then you also couple this reduced model to the solid, or
Yes. Yeah. So then we have an interface code that is just for the surface.
Okay.
And that code is actually useful because when you do surface catalysis, you might have surface transport of the catalysis process, and then you need that surface model anyway. So now we can reuse that infrastructure to do model reduction as well as surface catalysis.
Yeah, I'm curious to find out more. Yeah.
Thank you for the nice talk. Just to continue on this discussion on reduced order models. So obviously this space has like a nice base of literature and you have some analytic properties, but have you had any ideas about actually using neural surrogates for this? So neural networks?
The short answer is yes. The long answer is I prefer to use the physics that I have at my disposal first. And when I can't use those, then I'll go to something where I don't understand what happens underneath the hood.
Yeah.
That's my opinion. Your mileage may vary. Yeah, I'm a big fan of, if you haven't sensed it yet, I'm a big fan of linearized analysis Because it turns out if you do this right, it's really good. Now, obviously, it doesn't handle things like shocks and that, but you can learn an awful lot from this before you jump to a neural network. Or this can be what you constrain your neural network by. That is even more powerful.
Okay, let me ask something. This use case that you described with where you use preCICE for analysis, just to translate this a bit into preCICE language. So this means that you, like technically you do a volume coupling, right? So you have like SU2 on the one side, and then you have like a short Python script on the other side. And in the Python script, you write something to preCICE, which you then read in SU2 to modify your velocity values.
In essence, yeah. Yeah, so we do both surface and volumetric perturbations, depending on what we need. But for your volumetric example, with a flow solver or just a flow solver, just take a flow solver. If I do volumetric coupling, then if I perturb the state at one point, and I apply the right-hand side operator of the fluid solver, I'll get a new vector on the output. That is the action of the linearized operator on that perturbed vector. If I do a little bit of math, that I can convert directly back into the linearized operator itself. What I then do is I create a checkerboard pattern for all those perturbations. And I can do multiple perturbations simultaneously. Because if I think about a flow solver, it has a stencil. The stencil has a finite size. So I can perturb there, and they're independent of each other. And I take advantage of that. And then I schedule that in parallel. So I can do all of these perturbations at once through volume coupling. I can get all the perturbed states back, and then I stack all those perturbations up, and that's my big matrix.
Okay, and the getting back is again done via preCICE. So in SU2, you then write these values back to the
volume coupling, taking perturbed state in and a response vector back.
Okay, and then you write this to file, or you.
Yeah, or store it in memory, or we have a set of Python-based tools with like MPI for Pi and SLEPC for Pi, all these large parallel linear algebra tools that can directly take that information and assemble the sparse matrix.
Mm-hmm.
Then we can do eigenvalue calculations, resolving calculations, all those things we want to do with the data.
Yeah, got it. Thanks. No more, but I think we're also pretty much perfect in time. Thanks, Dan, again.